Good morning, everybody. Uh, Already you have learned a lot of things about biomechanics and implants. Uh, Already you have covered the hip joint, knee joint, shoulder joint, and many other joints. So, and also you have learned about the bone and to some extent biomaterials. But in this lecture, I will cover the biomechanics of spine and spinal implant. So first I will cover the biomechanics part of the spine. Then I will say something about the spinal implant and what is the state of the art research going on in this area and what we are doing also. First, spine, if you see that the spine can be divided into the three parts. First, this is the cervical one, this is the thoracic one, then it is the lumbar one, then it is the sacrum and coccyx. So, in these various parts, we can divide the spine. This is the sagittal plane view, you see. It looks like S. And this is number of S. And this is the posterior view. So those who are engineers, they can understand it, that it will be looking straight if you see from the back side of it. But in the sagittal plane, in side view, it will be looking like that. So you can understand it from the structure itself. There's a huge mechanics is related with it. Okay, because it can be straight. Why it has happened something like this? So we will discuss these things. But first I will discuss the cervical part. What is the cervical? The 7 vertebrae are there in this area. And it is huge flexible. You see this part, if you move the heads, you can understand that it is flexible. And what is the main goal of it? It supports the head. We know it. And wide range of motion that I have told you earlier. And it has the peripheral nerves to the arms, shoulder, and chest. That is distributed from here. Okay. Next, we will tell about it that I have discussed already here. Now, thoracic spine. What is that? It's the mid part of this. And we can say it's the dorsal region. And there is 12 vertebrae are there. And the ribs, in front of ribs, where the lung lies, actually it guards the lung, that ribs, and that is attached to it, main function. And you have already learned that rib are immovable joints. Rib does not move. So the vertebra, thoracic vertebra, is also to some extent immobile. Means it does not move. It is not that much flexible that cervical joints. So you see, you can easily feel it. And there is also some relative, or say that peripheral nerves are there. So it is the main thing of the thoracic spine. Next, the lumbar spine. That is the lower part of it. This is the lumbar spine, you see. And see that if you consider the thickness and the area, all these things are increasing. Why? That I will discuss later on. And there is 5 vertebral parts are there. Okay. And what is the main thing? It carries the weight, obviously the upper weight it has to carry. That is, so it is larger and broader than thoracic as well as cervical. It's larger and broader, means area wise, volume wise, it is bigger. And from it, the peripheral nerves, those who are distributing it, that is legs and pelvis. Okay. The nerves, that is peripheral nerves, that is legs and pelvis. Now, other 2 parts, that is also to some extent important, because that is sacrum and coccyx. Coccyx is that is not so much important, because it is the remnant of the tail. It's the obsolete one, the last one, the coccyx part, the last one. But this sacrum one, it is very important. Why? It is triangular structure, okay, and it is the base of the spine. Mind it, base of the spine, total spine it's holding, and connects spine to the pelvis. Always in the body, all the bones are connected somehow or other. Yeah, those are connected. The skeletal system total connected with each other. There is no, that is what I will say, that separate one, no. And it is making connection with pelvis, and pelvis to femur, femur to leg to the ground. Okay. So all these things, but now I will discuss that why this shape has come. Initially, it was not that. Initially, it was something else. Means in the childhood, just at 1 year, at that time 6 months, at that time, when we learn to see it, at that time, you see, at that time this will be something like this. But when we have become adult, we stand, then the shape is taking something like that. Okay, that is important. So initially the shape was not that. So it is depending on your weight as you are walking. So this shape has come. This is the optimum shape. Okay. So now if you see the compressive strength of the spine, if we will take each and every part separately, each and every, suppose if you take one vertebra here, one vertebra here, means it is cervical part, thoracic part, lumbar part. Okay. So what is the compressive strength? That is very important. By compressive strength, it has to take the body weight, and see it is increasing along this. Why? The weight he has to take, that is increasing, na? That cervical part only taking the head, and then the lower one, the body weight with its weight that it has to bear, that is increasing. So what will happen? I have told you, the nature has designed it optimized way. So it is also increasing the compressive strength. So you see that how it is coming, that from what I would say that 1500 to it is increasing up to, at the level, top level, if you see, it has gone 8000 Newton also. So that this load you can, this much load it can bear average way. And if you draw the stress strain curve, it is the general stress strain curve of spine. Any vertebra you will take, it will suffer from, and if you apply the load, it will suffer from a stress, it will provide you a stress strain curve something like this. Okay, that initially there is A to B, the, if you will see, the modulus is very low initially. Then you can understand that modulus is low, this angle is very less. But here, if you draw a tangent here, you will get higher modulus. So after some time, you will get the higher modulus. Then you will get, it is reaching to the plastic zone C and D, and the failure occurs. But initially, why it is low modulus? Due to cartilage, due to some fluid inside it. For all these things, you will see that deformation will be much. Okay. Now, the ligaments, that is very important. You see that what is the main function of the ligament? Is the controller of the movement. Okay. So when you have to control the movement, then you should have the strength, because it will try to go one side, you have to pull it back. So the strength is depending on that how much force you have to. So here the unique thing is that there is, you see, there is basically number of ligaments are there, but anterior longitudinal ligament ALL and PL the posterior longitudinal ligament, and LF the and also this CL the capsular ligament. What I want to say here, that here this ALL means this ligament at the cervical level, it does not need that much strength. Okay, so it is less, whereas CL means capsular ligament needs much strength, because here you need that more movement in this direction. Okay, so here this means it is depending on the how much movement, where which direction you can provide. Suppose if you see in the thoracic direction also, this strength, see, if you see that ALL, why the anterior longitudinal ligaments have the huge movement, because you have to go for flexion extension in the higher level, and when it will come, then this anterior longitudinal ligament will come into the picture. Okay, for your flexion extension. For lateral movement, the other things will take care of. So it is depending on the weight, body weight that is bearing, that ligament related body weight, I am telling now, ligament is not, vertebra is taking, and due to the motion, the level of tensile load is coming into the picture. That is the main thing. So why it is needed? When you are going to design the artificial ligaments, then you have to keep in your mind, because some people will come that due to ligament disorder they are suffering from some disease. Then if you have to replace it, and then you have to design it, then you have to think in this way, that what should be the thickness, what should be the material to be used, something like that. So this slide is very important for your understanding, that which ligament will provide which type of need, which type of strength, or which type of tensile or the forces it will suffer from. Now, that how this motion takes place, why we are getting that much flexibility? Because if you consider there is two parts, okay, that vertebral part here, and in between there is a disc part. Vertebra itself cannot move, you know, that is a solid one. But the disc, I will discuss later on detail about the disc that I am coming. And there, the main flexibility we are getting for this disc, because I will discuss, because this is a soft part and that is actually providing you the movement. So, and what are the degrees of freedom we are getting here? That most of the cases, you know, that flexion, extension, lateral movements, all these movements we are getting. So, actually axial rotation also, if you see in this way, we are getting the axial rotation. So, all these things we are getting here. So, there is movement wise it is flexible, but you cannot move at any range. No, there is certain constraints are there, not more than that. And who are taking care of that? Movement restriction, ligaments, the controller. Okay, so you know it already, you have learned a lot of things about it. Now, I am telling you that when this motion will take place, then what happens? Obviously, suppose you are taking this. Okay, what will happen? A movement. This will suffer from contraction and this will suffer from an extension. But it is obviously there is fibers, I will discuss later on, and these fibers, it will happen something like this, for this that will come, and if you take the sagittal view, if you take the sagittal view, if you take the side view, the fibers will look something like that. Okay, but if you take the anterior view, backside view, then you will get that fibers are something like this. Okay, and when you apply the more load, it will try to horizontal means there is an angle, you see there is an angle here. Okay, and it will, the more load, the direction will be, it will tend to the horizontal direction. So that is the beauty of this fiber, what I will say, that orientation with the movement, how the orientation of the fiber changes with the movement, that the later on. Now, if we see the rotation, the movements, intermotion in the movement, it's very important slides. How much, what is the degree of, how much, because all these things, it is mentioned by the angle. You see, it is mentioned by the angle. What is the flexion, extension, lateral flexion, and the rotation? All these things are quantified by angle only, because you see, actually these are the angles. You are looking that there is a, what is it, translational movement, but it is not that. Actually, due to some angular movement that is happening. Okay, that is clear to you now. So here you see that it is not the regular, that all vertebrates are suffering from for anything that same level of angle. No. For the particular purpose, that here you see that flexion, extension, this part means that cervical part is suffering from close to 15-16 degree movement. Okay, you can take each, it is not that as a whole, each part, if you see that, and here you will get the actual thing, that which angle this slide will provide. thoracic part, it is to some extent immovable. I have told you. You have taken that is maximum 7 to 8 degree. Here it is less in the direction of the flexion and extension. The thoracic part is suffering from less movement, if you see. Whereas lumbar part is suffering from more movement in the case of flexion and extension. Okay. But in the lateral, you see, it is suffering from that. Yes, you just think that here the movement is less when you are moving in the lateral direction. Okay. And thoracic direction, obviously, it is less. But always there is more in the direction. And also the axial rotation cases. Here, see that for this, it can rotate, you can rotate this part more or less. But at a higher level of rotation is here. So it is more than 20 degree, you see. And later on, this is the. So this slide will give you the entire idea about the spine motion. So this is very important slide. You can keep it. I will tell Sanjay that the biomechanics part of the you can get it. Okay. So if you see that just this slide, this is enough for you to understand regarding the movement in detail. Okay. Now, is the same thing. I will not go to the detail that that is in another way that has been represented. Now, that weight bearing, this is very important thing because actually the disease, we are suffering from different type of disease. Due to mostly the case is weight bearing. One thing that is osteoporotic type of thing, okay, that is if your weight is less, then if you are to some extent osteoporotic, you can survive. But if your weight is more and you are suffering from any type of bone disease, your life will be hell. It's a huge pain you have to suffer. So weight, but nature, but it is what I want to say here. So you have to understand each and every part of the vertebra, because you will see they are bearing different level of weights. One thing. And number two, that is important, accordingly, this, what I will say, height as well as the area is changing. Its structure is changing. And I cannot go to detail of it because I have to speak a lot of things about the spinal implant. But this intervertebral disc, the cushioning effect, and see, vertebra is strong enough, but the beauty of intervertebral disc is that it is soft, but it is bearing the weight. So when people are suffering from disease, most of the cases they are suffering from disc problem. That I will tell you later. Now, regarding the disc, I will say that it is soft fibrocartilaginous cushions. It exists between the two vertebrae. Okay, allows some motion, and total 23 discs are here. Why? 24 numbers of, so if between two discs, two vertebra there is a disc, so 23 discs. And lengthwise, the 1/4 of the spinal column length. Total the length 1/4 of it. And it is avascular, means there is no, what I will say, that vascular system inside it. How they are getting nutrients? From the end plates, meaning from vertebra it is taking. Okay, nutrients. So I'm going to detail of it. That already I have told you regarding this, and it is act as a shock absorber. Now, what is the main thing? That it has a middle part, there is a nucleus, that is softer one, and there is a fibrous part surrounding it. Okay, and the fibers, if you see that it is making an angle. When it has to bear more weight due to some specific condition, then what will happen? It will become horizontal. It is strong, radial, tire-like structure. Yes, just tire. If you have seen the tires, that is structure. Concentric sheets of collagen fibers that I have shown you already. That is concentric circles of the collagen fibers. And encloses the nucleus part that I have told you already. But you see there is an angle. Okay. See, it is very common when the bending will take place, tensile force will one side, another side there is a compressive force. In rotation, what will happen? Obviously, reorientation of collagen fibers. When this thing will happen, that collagen fiber has to make an angle. There will change of angle of collagen fibers, because you can easily understand it. And tightening of fibers traveling in one direction and loosening of the fibers traveling in opposite direction. Okay, one direction will be tightened, obviously another direction it will be loosened. And it has some water and proteins, and the proteins attract and retain the water. It's a hydraulic gel-like matter. Yes, you can say. And regarding, and it is viscoelastic, that I have not written. It's a huge viscoelastic, means its viscosity is very high. Means everything is, we are considering as a elastic, but everything actually is viscoelastic in the world. But when elastic property dominates very much, then we will consider it as a elastic only. And its viscosity, viscous property is very high. That I can say. And there is a huge water inside it. But that varies throughout the day. It's not that the constant amount of water inside it. Okay. In a day, it varies. Where in the disc part, the water content varies. And what is things, when the pressure will come, obviously the internal pressure will increase, and there is, due to that there is lateral forces that will come into the picture. And last part is very important, increased stiffness. That is the viscoelastic I am telling. What viscosity means? That its stiffness will depend not only on the load but also on the that load speed, means how much speed you are applying the load. Means it is, what is the technical term? Not on the strain but on strain rate. Higher strain rate, it will provide you higher stiffness. Okay, so that is there. it is something like that. If the weight, the if the force will apply, if there is a constraint, the bulging shape it will take. Okay, and the if the weight is eccentric, then it will be something like that. The angle I am telling you that highest it can reach 15 degree. Huh? So from this way, more the weight you will apply here, this fibers, angular fibers angle will be changed. More the weight, the angle will be more. Angle will be more. More the weight, angle will be more. Highest it can extend to 15 degree. I am not going to detail of these things. This, if I want to explain the chart, it will take a long time. So I am avoiding it here now. Then creep characteristics is there. Means if you keep the load for a long time, strain will not remain same. Strain will be higher. Okay, so it has creep property that is very important for you. And also the shear and tensile characteristics. Shear stiffness is 260 Newton per millimeter square. See, this magnitude is not that much important, because when you have come to learn the mechanics, then the fundamental is very important. That what is happening actually, it can be explained, but the magnitude is not that much important. I'm not going to that way. And if you see the what I will say, that compressive load characteristics, that cancellous bone part. See, there is two parts in the vertebra. One is the cancellous bone inside it, and another is the cortical bone, the outside it, the structure. This cancellous bone deformation can take place 9.5% before failure, while as the cortical bone is the allowing a small deformation, that is 2% only. It is more or less same for the all parts of the body. It is not that for this. Okay, I will not tell detail about the load of the lumbar spine, because in which posture, what is the amount of load it will suffer for a person 70 kg, that much that I will say. So where it is load, the third of the lumbar disc. Third lumbar disc means between L4 and L5. Yes, L4 and sorry, L3 and L4. So if a person of 70% weight, if you just lie in this way, it will suffer from very less than 25 kg or something like that. If you also in this direction 75, if you stand, then it will suffer from close to 100 kg, because due to some, you cannot stand in 7. So the CG will act, so it will be more. And if you go something like this, okay, if you stand, then the third lumbar disc will suffer from 150. Already you have learned that when a person walks, at that time hip joint is suffering from 3.5 times of his body weight, more or less, close to that. So you have idea that when people are doing their regular activities, or the walking or running or all these times, then any parts of the body weight, lower part especially, is suffering from times of the body weight load. Okay, you know it already, na? So it is not new to you that you will be not astonished. That first time when I come to learn it, that I was astonished that yes, that much load is coming. How? Then I come to know that why this moment will come, that inertia force, all these things will come to the picture, then that will come. So you know about it. So in the different postures, if you see, you will it will suffer from this type of load. And when you will sit, obviously that will come down. But after sitting, if you take something different posture, again the load will be higher. You see, the last time it is more when what you are doing actually, you are sitting and in this way. This, the body weight that, if you see the momentum, that is increasing. Na? You see that suppose this part of the CG is here and the momentum is increasing. So you are suffering from more weight. So that is the thing that you have to understand, that for different position, how the load will change in the disc. And see that it is disc load means disc is soft one. You can understand that this softer part and made of protein and water, etc., that is suffering from this stuff, this much load, and it is taking. Okay, so it is the what I will say, that really I do not know. It is, you can understand that, and it is very light. You see, light. So it's a unique thing that. But if you want to engineer it, means if you want to make it something like this, how much tough it is, you know it. So it is not that much important that if you want to measure that how much force there is, you have to measure in this way, that needle pressure transducer is there, okay, and you have to put it inside, and if you give the load, you will get that pressure. And I am not going to the detail of that injury it will suffer. It is a something else. I will. It is better you should learn it from a doctor, because I am not confident about that which type of injury, because injury case does not come. It happens to my life. They see when some students come to me, say, actually you are working on this area. What I will say that in the implant area. Yes, my mother is suffering from this. Okay, no. For that I cannot give you consultancy. Only thing I can say, you go to the doctor. In the design, etc., that I am ready to do, but I cannot advise to you. That I do not have that right. Okay, this type of disease. It will suffer from the fragmentation of the nucleus populace, which inside this material come out. That is one type of thing. And I will, for this type of disease, I will not tell you data. Okay, so I feel that the biomechanics of the spinal implant part, we can close it here. And what I want to say in this class, that take home message, that three parts. Here the muscles is not that much important. The ligaments are important, but other cases the muscle is very important. And here the disc part is more important than vertebral part, because most of the cases people are suffering from the disc problem. Also for osteoporosis there is vertebral problems also that happens. And the most important thing, that its shape, size, all these things are depending on the movement and the load it has to bear. So it is not only true for the spine, but for the whole body skeletal system. And how this is applied in the spine, that I have tried to deliver in this class. Thank you very much for this. for after 40, 45, then or 60 years. Now we are entering into the part B, that is the conceptual design of a novel spinal implant, a biomechanical study of artificial cervical plate and intervertebral disc. Whatever we have learned in the last session, we will apply that knowledge when there will be a spinal disorder. In this lecture, first we will try to understand what type of disorder uh, the patients are suffering from and what is the remedial measures that surgeons are taking except the conventional medicine. Now, firstly, I am telling you here I will move to some extent fast because due to the time constraint. I will try to give you an idea that which type of research is going on in this aspect. That is the main thing. In this lecture, I will give you the problem description, then state of the art, what is the literature survey, and then what we are doing. Then I will discuss the future scope of work that we have learned. I am not going to the detail of this. There is two type of injury, whiplash type of injury, because due to sudden fall, road accident, all these things, and there is degenerative disc injury. Okay, the disc and sometimes the degeneration of vertebra may take place. Okay, both. Now, here you will get a good idea that if it is the normal disc, there is a degenerated one, there is a bulging one you see, there is thinning of disc, all these things are happening. So main thing is that it is suffering, the disc problem is the main problem. Okay, sometimes the vertebral problem also take place. Now there is different type of remedial measure can be taken, physiotherapy, all these things. But this arthroplasty, and we will discuss that discectomy without fusion, and also we will try to understand what is PDN device. Okay. See, what is the disease actually? Here the problem lies. So, in the cervical cases, how we are combating those challenges, that is very important. What is happening? This is compressed, okay or not? So what is happening actually, due to this, there is nerve roots are there. I will explain it later on very well. So if the nerve roots become compressed, then what will happen? You will suffer from pain. That is the point actually, I will come later on. So what we are doing? We have to keep that gap open. Okay. We have to keep that gap open. This gap we have to keep open. So what we are doing? We are providing these things. See there, screws we are making. There's one plate, and here we are making another screw, and we are putting those screws. What this plate? What is the function of this plate? This is keeping this distance constant. Try to understand it. Okay. So main objective of this plate, I am coming later on, that objective of the plate to keep this distance into a certain level. Okay. So what will be if this distance will go down, then nerve will be compressed and you will suffer from pain. That is the main thing. Okay. And we will discuss it throughout this lecture again and again. In the posterior view or lateral view, we can say. Here, this. Now, spinal fusion surgery, it is called the spinal fusion surgery. So, it is, if you put this type of thing, then what will happen? There will be restriction of motion. You cannot rotate because you have put those things. Huh? So, that is the main problem. So, what we are doing? We are trying to replace the disc. That I am coming later on. That is a newer concept of arthroplasty. That is the disc degenerative disease. To avoid that, we are putting that artificial disc so that patients will experience pain relief and return to the function. So what is this disc? This is the disc. Here we are putting one part, another part. I will go to the disc part again with detail. So what is the, why we are keeping this disc, or why we are putting some, what is that fusion plate here? Because to remain this gap open. What is the function of the gap? Nerve roots are coming out. I am not going to discuss this literature with all these things. I am going to the, so these are the different level of the cervical spinal implants. Okay. And what I will say, that here you see that always to keep this gap, we are putting we are putting this plate and these two screws. Here also this. The different types of available, different types of spinal implants. Sometimes we are using it lumbar, but all the things, the main objective is that to remain this gap constant. Okay, here also. I am not going to the detail of the literature survey because it will take time. But what I can say that there is a huge development occurs in the 1980s and 1990s, and still now the development is going on. During 1990s, what happened? There is a two types of development occurred in the other direction. What are those? In the image processing technology, we have developed a lot. Number one. Number one, in the manufacturing technology, we have developed a lot, means rapid prototyping, additive manufacturing technique that has come. And it has regularized, or I say that revolution occurred in the case of treatment. Okay. So, due to development of technology in these two aspects, given us confidence to treat this spinal disorder in a separate way, in a different direction. And this is the different type of artificial disc. These two parts, one part here, one part here, we are putting into the vertebra, okay, through this. And in the intermediate part, here, there is a ball artificial disc, means there is an arrangement that I will show you later on. Here, this arrangement is there, okay. So, what will there is concave part and there is a convex part, and what it is allowing? It allows the movement, means angular rotation, okay. So, this is very important. And now we are sometimes trying to replace it by this type of gel type material, but it is still now not that much popular. First, if you have to design it properly, one of our PhD students worked in this regard, and what he has done, he investigated what you need first to design it. You have to investigate what is the shape and size of it, how it can be. Yes, it was not possible before the CT scan came into the picture. It's not possible. So, from the CT image, we can do it. How? CT image, and there is an image processing software Mimics. Already you have learned a lot of things from Mimics, okay, probably, because. So, this is a typical vertebral body, and you have to know the dimensions of the patient. Patient to patient, these dimensions will vary. How? You can see it through this CT scan image. And here you see this is all the dimensions, important dimensions we have tried to find out. Okay. these dimensions you have to know properly. For a patient, you cannot do it in this way, see you cannot bring it out and then you can see and then you can insert. No, it is not possible. It is possible only getting CT scan data. And that we are doing, we have done the CT scan of this patient, and from this we are taking this. What is this by PL means pedicle length. This length is very important. This is called the PL. And PL left and PL right. What does it mean? This means this length, this length. Sorry, this length, this length, this length, this length. It is very important to design. Sorry. So we have given some nomenclature of it. Suppose pedicle length, pedicle width, pedicle height, all these things you have to mark and you have to see. Then what you have to find it out? The intervertebral disc area you can mark in the CT scan and you can measure it. Okay, by using that mimic software. And here you can measure the height also. Here you can this thickness also means this breadth also. This vertebral body depth, VBD, they are considering it in this way. Okay, so in this way we can get the measurements of the all dimensions. Then these are the nomenclature that pedicle length that you have seen, and we have plotted it. What we have done actually, we have to, what is our objective? Our objective is to design a proper implant. And where we will insert those implants? In that body. So you have to have a very good idea about the dimensions of these things. And so to know the dimensions, what we are taking the CT scan of the number of patients. Okay, and you have to identify that what is the range of dimension, and accordingly you have to make the. So we have put those dimensions. I am not going to the detail, it is a comparison, but it will not give you anything. But what happened actually, we have taken different dimensions and we have done the mean, standard deviation, max, mean, etc. I am not going to the detail of it, but the thing that I want to say that here you will get some graphical representation of it. That PL means pedicle length. What is the pedicle length? And PL R, PL right. Just one example can help you to understand that. If I will go further, yes, this is the PL, means this length is very important, okay, for designing the implant. So that we have taken the number of patient CT data and we are putting it into the graph. And what we are doing for C3, the dimensions are something like that. What is the PL left and PL right for male, and PL left, PL right for female? Yes, these dimensions are not same. First, what is not same? That PL right and PL left, that is not providing the same value. You see from this curve, you can easily see it. So it is true for all the dimensions. All the dimension means, if I will go further, see, it is also the width, length, means PW PDW means pedicle width. Okay, so that dimension it is also changing with time. Now I am not going to explain these curves each and everything, but what you should know that these dimensions first you have to find it out, otherwise you cannot design it. Then I am not going to the detail of, because there is a lot of things I have to cover. And here that area, yes, yes, that the area of the vertebra that we have plotted, and we have tried to find it out. If we want to place a disc, what should be the area of it? Okay, I've shown you earlier that here, sorry, here this area. If you do not know the area, then you cannot design the disc properly. No? So that area we have find it out from the CT scan data, and we have done it. Now, what the friction where you leave it, this part, and here how we are developing the implants using Mimics, SolidWorks, and ANSYS. These are the CAD models of the implants. Okay, disc. This is the fusion surgery. Okay, no motion is possible, and this is the disc surgery. Okay, you can put a disc. How it works, we have modeled it, and if you put the disc in between, we have to put it here, we have to screw, and inside that will be there, and this will be the. So this you have to simulate first. How? From CT scan data you will get the model, and from that you can simulate it, your disc, design your disc. These are the different part of it. What is this? This one is metallic one, and this one is made of ultramolecular weight polyethylene, and this part is metallic one. So this part, if this part is convex, then it is convex part. One part will be convex part, another part will be concave part. You can put it anything. What we are doing, first we are taking the CT scan data here, and we are modeling it in this way. Okay, we have got the 3D model. From that, we are making a, already you are known very much familiar with these figures, means this type of CT scan data from that modeling. I am not going to the detail of it. So we have to model it in this way. Then we have to go for a finite element analysis of it, means finite element modeling of it, and then we can get, by rapid prototyping, this each and every vertebral dimension actually. Okay, and that we have made in our lab. Means in the lab means in the CME at Durgapur, there's one PhD student who is working. He has made those things, and he has put this disc here in this way. You see? Okay, you have got the idea. Okay, now here we have taken different type of bone condition. Why we have taken different bone condition? Patient to patient, the bone condition varies. So we have taken different bone condition. That is, one is the normal bone. Another is, we have seen, that is 10% weaker bone. And 10%, suppose we have taken 50, 60 numbers of CT scan. Here we have taken 51, probably 51 or 52. And there we have got some, the average one we have considered as a normal. Okay, close to the average one. and we have considered one is 10% weaker than that, another one we have seen that 20% weaker. We have taken those and stronger series data, and we have implemented this two models. Means one is fusion type model. I have told you that is plate, only one plate, and there is screws. But what is the problem with it? It will restrict the movement. That is the point. But here we can put the disc that will provide you the movement. But there is problems also. And we did this, what I will say, that finite element analysis, and we have given which type of load. For flexion, extension, this type of load we have applied. Forward flexion, forward extension, left lateral bending, all types of load we have applied in that model. Okay. And also we have applied the combined loads. Okay. That FE plus CR means forward extension plus counterclockwise rotation. All these things we have applied in this model. And we have observed the results. For two things is very important. When you will design the spinal implant, two things is very important. What are those? Range of motion means how much motion it is providing before implantation. What is the gap between natural one and the after implantation? Okay, range of motion. It is definitely for spinal implant. And another thing is that how much stress it is suffering from. Means normal bone is suffering from one level of stress. If that after implantation, if the total stress scenario has been, if it has been changed, then there will be a problem, huge problem. So we have to design the implant such a way that after implantation, that stress and stress, there will be a difference, huge difference with natural one. But we will try our best to keep this gap closer. Okay, less. We have to. So we have tried with this, and see, we have compared that natural spine, green one, spine with fusion, that is providing very less. Okay, and it is, so it is a total angular range of motion. Okay, and this is providing close to natural one. So if you go for disc replacement, that will give you better result. We have observed it. Okay, but the problem is there. What is the problem? That the operation of this replacement is very tough. That we have to understand first. Okay, this operation is very critical. Okay, so surgeons are avoiding this replacement, but now the technology has developed a lot, and that aspect that people are doing. But that is the point actually. Now, here the stiffness, if you see, the stiffness, yes, the spine with spinal fusion, it is very high. Okay, the stiffness obviously is much stiffer. That fusion surgery will give you, but the natural one is very less, and the stiffness will be higher also, if to some extent higher, if it is total disc replacement. Okay, so this is that was the graphical representation. This is another type of representation. I am not going to, if you can understand it, I do not have to go for that. Now, actually now, I do not want to show you this, but just one thing I am telling you, the when suppose you have put the your implant between C6, C5 and C6. Okay. Then what will happen that other disc means C2, C3, C3, C4, C4, C5 and C6, C7, C7, T1, all the cases that angular movement will be more than natural. Try to understand my point. Only C6, C5, C7 that is fixed means implant you have already put. So that is fixed. There is no movement on that part. See here it is red means it is very less. There is no obviously. But what is happening you see that other in C4, C5 it is more. C3, C4 it is more. So if you place one implant, fusion implant at any level, then for the if you want to move, then the other disc displacement will be more. Root means degree of motion will be more. But resultant will be less. Why? Because here it is very less. Okay. So that is the one thing that is to be understand, that for the fusion cases, because fusion is, what is fusion? Fusion is making huge movement constraints. Okay. Now for other cases means for the spine with this displacement, if you see here there is no change of movement, that is quite close to the natural movement. So what will happen if you put the disc, artificial disc instead of fusion, that from the range of motion point of view it is closer to the natural one. I am not going to the detail of it because it is not needed. I cannot explain that. That what we have done the finite element analysis of it, and we have seen the result, that is the stress strain results. Okay, and it is the displacement profile, leave it. Yes, it is the stress profile. What we have observed actually, that if it is a spine, the more the load is 2.4 Newton load, more the load, more the stress. That is important. And for different type of movement, if it is forward flexion or it is a forward extension, forward flexion, lateral movement, if you see in this direction, that for different cases you will get different types of load. I have already discussed that there is a different types of posture may come. Suppose if you do in this way, what is this? This is the front flexion as well as there is a rotation. So the load will be more that case. So we have studied all these complex cases and we have observed the results, that where how much stress is coming. Yes, for the case of when the combined load will come into the picture, here the stresses are higher, you see, more or less higher. So we have to understand it properly. And now if we see here, we can see the result that due to implantation where how much stress is coming into the picture. The what I will say, that take home message is, more the If the bone is stronger, stress will be more. But that is not a point of concern. Why? Because strong bone can sustain with more stress. But what we have observed, weaker the bone, the stress may be less, but it will suffer from more strain and failure occurs. So obviously, when we will design the implant for stronger bone, then we do not have to think much. But when we will going to design for weaker bone, we have to think twice, means we have to change the design. So that is the research that we are doing, that if the bone condition changes, that what should be the change in the implant design. Yeah, only 15 minutes left. Just observations I will read. Two types of implants that we have discussed. That is fusion one, and another one is disc replacement. Just we will compare with those. Natural spine has maximum freedom of movement, obviously, but which is highly restricted with final fusion surgery, but little bit restored by total disc replacement. Okay. The maximum displacement value is not constant, but it changes for different neck movements in a natural spine. However, after implantation with both fusion surgery and disc surgery, the displacement values become more or less same for all different neck movements. Okay. Now, observation about the stress. The stress values in natural spine for different neck movements have been found to be much smaller compared to those in spine with fusion surgery and spine with total disc replacement. That is the another thing. The stresses produced due to different neck movement under load have been found to be almost constant for natural spine and varying with a small range for spine with TDR. Means the stress values in the bone after total disc replacement, it is to some extent closer to the natural one. But in case of fusion surgery, the last one, it has a huge difference with the natural one. It is higher because you are inserting the, what I will say, the screws, as well as you are restricting the movement. These two are very crucial. Restriction of the movement means higher the stress. Okay. And observation of the strain, I will, that is to some extent same of stress response. Now, and we have compared the stresses at the different levels, and I am not going to the detail of it. Okay, it will be a long time, and we have tried to design a new type of cervical implant in this way that will provide you the, to some extent, stiffness as well as some flexibility. That is this type of thing. We have introduced a spring and we have introduced something that I will tell you. We have modeled it in this way, and these are the things that we have tried, and you will get those things in this way. And we did the finite element analysis of it, and we have made it also of plastics, means multimolecular weight polyethylene. So we are thinking to design a different type of implant in this regard. Now I am not going to the discussion because I have to. Then whatever you have seen, that is the lumbar design part. Okay, and now I will discuss cervical part. I will discuss the lumbar implant now. Okay, in the lumbar part, that here I will tell you that lumbar part is the same thing, that there is two discs, between there is a disc, and we will discuss that what is the problem that I have discussed earlier, that these nerve roots, if this gap will be less, then we have to maintain this gap. That is the goal. Okay. Now, these are the pedicle screws we are going to use here in this model. This is the disc, and this is the, why we have kept this part. Previously we have seen we have kept it stiff, means there is no movement. By this arrangement we are trying to provide some flexibility. Okay. Now how we are moving? The objective of this, that we have to compare the two types of implant, that is the fusion type using pedicle screw, and disc type, the same thing. How we are doing this? First we are using the CT data, you know, and from this CT data, first we are separating out the bone part. You have learned now already these things, that from CT data how to model it. It has been discussed here. Okay. So the same way we are modeling it, you see, and the same way that discussed here, we are assigning the material property here. Okay. This is the material property, location to location, the material property of bone differs, and how to allocate that in your simulation from the CT scan data, that is, it will provide Hornsfield unit pixel value. From pixel value you are getting the density, and density to Young's modulus. You are putting that. Already you have learned it. So we are assigning those things. Then we are putting those screws here. Okay. Here we are putting those screws. You have seen in this model. And here also we are putting the ligaments. And the different ligaments has different stiffness value, that we have put it from the literature. Okay. And now we have also put the disc also. Okay, here. This is the disc that we have, artificial disc. And we have observed the results. I am not going to the detail of the material properties, etc., because already we have learned a lot of things regarding that, how to put the material property of the titanium, multimolecular weight polyethylene. I know that in this. So I am not going to the detail of it, but what we have done actually, we have taken different type of screw. Suppose 4 millimeter, 5 millimeter, 6 millimeter screw, and we have taken different type of load, body weight. Okay, that is 420 Newton, 490 Newton, 586.6 Newton from our literature. And we have taken different screw material, titanium and stainless steel, etc. And what we have taken, different type of bone condition. You see that 5 type of bone, that is the normal one, B1, standard, then 130% of the B1, close to that, another 105% that is strong bone, 90% that is weak bone, and 70% that is weaker bone. So how the result varies for a particular implant and what should be the optimum implant for 5 bone cases that we have observed. So what we have observed actually, we have these are the ligaments stiffness value that we have put, okay, and total 90 numbers of models we have analyzed to get the optimum solution. Okay, you can see if you vary the screw diameter into 5 types of bones for each cases, then 2 types of materials and 3 types of body weight. All these things are going to, if you multiply each and every parameter, it will come more than that. We have chosen someone. Then we have what we have observed. That we have observed that if the bone condition is weak, then that stress is less, okay, and the diameter is less, the stress is more. That is the obvious point. And it is not the important the stress in the pedicle screw. See, here we have seen the pedicle screw. It is not important for us, important. But what we have observed, implant does not fail. It fails rarely. Usually it does not fail. It loosens. So the failure of implants occurs. Bone cannot grip it properly. That is the main cause of failure for the 90% cases. So what we have to observe? We have to observe the stresses at bone. Okay. If or strain at bone, if after implantation strain at bone is favorable for osseointegration or not, means after implantation how much strain is generating in the bone, means surrounding bones, that is very important. So that we have tried to observe. This is the implant, what I will say that. But here you see we have tried to find it out, the what is the stress and strain condition for the bone. So what is the take home message you will take? Yes, the implant stress is important one, that you have to see, check that it will fail or not due to that loading, but most of the cases it does not fail, rarely fails. But the important is the stress strain at bone, surrounding bone. That is more important. So we have observed it and we have find it out that conclusion that we have done conclusion in this regard. And in case of what I will say that artificial disc replacement, we have observed some values. There we have to observe the stresses at ultra high molecular weight polyethylene. For disc displacement, the condition, the situation is different. What is that? Their failure occurs due to the degeneration of implant itself. There, the stress strain condition bone is important, but more important is what is the stress and tribological condition of ultra high molecular weight polyurethane. Most of the cases we have observed degeneration occurs at ultra high molecular weight polyethylene. So we have tried to observe that how much stress is occurring at ultra high molecular weight polyethylene. Okay, so that is our goal. And here we have seen that we have tried to design that for just, we have seen that for 5mm screw, no distinct pattern of change in strain due to the screw material is observed. Okay. For titanium screw and for stainless steel screw, we have not seen much difference of strain, means at the bone. And we have studied also the range of motion. Obviously, case of uh, if you see that natural one movements are more, but if you observe the, what I will say, that for the fusion and for the, what I will say, for the disc replacement, the movement is less. Okay. For all the cases that is happening, for lateral bending, for flexion extension, all the cases, what is the general thing we have happened? The movement point of view, in case of lumbar also, after replacement, if it is fusion surgery, range of motion is very less. If it is disc replacement surgery, the movement is more, but not close to the natural. Sorry, I'm going back. And range of motion we have studied. I am not going to explain all these curves. That what is the effect of ligament? All we have to study actually. Okay. The conclusion part is that okay, what I have told earlier. Just one thing that I have to. We have designed a new type of implant. Actually, I have to move fast. I have to go the other part. I will say something about the impact biomechanics, then I will finish this part. Okay. The spinal impact biomechanics that we have studied. There is cases we have seen, there is two type of fall or two type of accident occurs in the case of, in close to the pelvic part and as well as in the spinal part. That accident occurs due to fall and the slip. Fall, backward fall, sideways fall, and motor vehicle accident. If the side impact is concerned, the most of the cases we have observed that failure occurs here, and if it is side impact, a side fall, then the failure occurs this greater trochanter to lesser trochanter side. Okay, that is the data, and in our results also we have got it. How? We have first modeled the, from the CT scan data, we have taken the CT scan data to the pelvic part as well as the lumbar part, okay, and the sacrum part also, and we have modeled it, and we have stacked one after another. We have got the model. Then we have gone for a finite element analysis, finite element modeling of those models. Then we have put the soft tissues from the same CT scan data. Then we have simulated this type of falls that may occur, and you will see that simulation is not occurring. Right? Okay, that it is not occurring, but why simulation? Okay, I will. but this type of what we have seen in our results, that from the clinical report we have got that here failure occurs, and we have also observed the higher strain at that level. So what we have done, then it is clinically okay, but what you have observed? But we have observed that how much force is coming. That is important for a standard weight. So how it will works? What is the application of it? If you have to design the carpet, or if you have to design some pad, what should be the thickness of it? That we have designed actually. Here we have simulated different type of fall, different angle of fall, and I do not know why this simulation is not occurring. It's not happening. Why? Okay, later on we will check. But here also we have simulated this. You can get the shock waves, that how it works. That this fall we have simulated. You are not getting the simulated good, otherwise you can understand it properly. Then what we observed actually, we have observed also that huge amount of strain here also, that we have seen that failure occurred that part, and the same part we are getting the maximum strain. And we have designed also the car door. We have simulated the car door, and we have taken some safety measures. We have observed that due to, we have seen that in the last year a clinical report that here the failures occurs due to side impact, and we have also observed the same thing in our simulation results. You see here we are observing the same results, okay, at this part, that maximum strain is occurring, and we have quantified it, that how much strain is coming, okay. So, and we have tried to from car safety design, car door safety measurements we have designed, that we have given some foam pads, etc., and we have seen the results for this, that how is the effect for this. Now lastly, it is unfortunate that I am not that simulation is not occurring here. If it happens, then you can understand it easily, that how the stress scenario is changing due to impact. Now the last part of it is that we are getting to replace the nature. Is a very tough job, okay, but we are getting a ray of hope to face these challenges by the help of nanotechnology, nanomaterials, etc. And we are yet to go long to fetch our goal, because the still we can understand it properly, that if we want to go to the close to the nature, something we have to engineered that is close to it, this is too tough job, and we are far away of it, but definitely we are moving ahead. We are moving in the right direction, but it is too tough job. Now thank you all for your patience hearing.
Done. Suraj, बोलो. Good morning, everyone. So this is the talk in continuation with our previous day's lecture. So now I'm going to talk about different type of permanent implants, specifically the composition and their utility in different type of implant fabrication. So I think yesterday I discussed about the ceramic implants. So today I'll be talking about metallic implants and the different type of polymer implants. So amongst the different metallic implants, as we know, one of the earliest introduction was stainless steel. So stainless steel was used from 1930s onwards, as we know. So one of the composition of the stainless steel is 18-8 or 302 stainless steel. So here as I see, the iron content is about 100 minus 26 weight percent, chromium is about 18%, nickel is about 8%, and carbon is about 0.08%. The stainless steel for 18 weight percent chromium and 8 weight percent nickel is added to make the stronger steel and of course to impart the corrosion resistance property. Specifically, the body fluid has a huge concentration of chloride and sodium ion. So these are really corrosive environment. So corrosion resistance is one of the most important part, and also the nickel is a austenite stabilizer. So to improve the further corrosion resistance property, metallurgist has introduced some amount of molybdenum. So molybdenum addition improves the corrosion resistance property, and then again further modified to 316L stainless steel, which has the carbon reduced from 0.08% to 0.03 weight percent. So it has further improved the corrosion resistance property because of there is a chloride solution in the body. So as you can see the composition here 316 and 316L. So there is a major difference is actually the carbon, which is 0.08 further reduced to 0.03, and in case of 316 and 316L there is some introduction of molybdenum, which is about 2 to 3 weight percent. So as you can see here there are list of alloy. So alloy is solid solutions. So list of alloys are having very different elastic modulus. As you see here, cancellous bone has the elastic modulus up to 30 GPa, whereas nitinol has the lowest elastic modulus amongst most of the metals, which is about 48 GPa. And you see the commercially pure titanium has the modulus is about 200 GPa. Commercially pure tantalum has the modulus is about 200 GPa. Commercially pure titanium has the modulus about 100 GPa. And you can see there are series of titanium based implants materials are developed just to reduce the modulus to avoid the stress shielding effect. I am not going into the details of all the different alloys, but what I would like to say, the one of the most popular alloy even today is Ti64, titanium 6 aluminum 4 vanadium, all weight percent. So here I can see, as I mentioned last time, that Martin-Jadek transformation. So alpha phase of titanium is actually a hard phase, while beta phase of titanium is actually a soft phase. If we have a composition where you can have the combination of alpha and beta, so alpha can give you the strength and beta can give you the toughness. So that is where the role of aluminum and vanadium. So we choose the composition in a way that we get alpha and beta both. So we are adding the aluminum to the Ti64, I mean to the titanium, commercially pure titanium, to have both alpha and beta phase, and similarly the vanadium. So as you can see from ternary phase diagram, the titanium, vanadium, aluminum, and this is the desirable composition where you have both alpha and beta. So what we can see here, during the processing we have the beta phase. Just by following different type of cooling rates, we can have different type of microstructures. So could be lamellar microstructure, could be basket like. We can have both combined alpha and beta, that is required to have strength and toughness. So here aluminum actually act like alpha stabilizer, but zirconium, the vanadium actually act like a beta stabilizer. Okay, so aluminum act like a alpha stabilizer, while vanadium act like a beta stabilizer. And as we know that titanium has tendency to oxidize, and in the electrochemical series we know that aluminum has more tendency to oxidize than titanium. I mean, so that way the aluminum can oxidize to have a oxide coating on the surface. So beta phase, as I said, improves the wear resistance property, high elasticity, and excellent cold and hot formability. So easily we can deform into different shapes using beta phase of the titanium. So there are different beta stabilizers, for example iron, vanadium, tantalum, niobium, molybdenum, nickel, chromium, copper, etc. So as you have seen, there are a series of alloys where they have added different elements to have different beta phases. So this is very interesting, that as you see here, titanium, Ti64, cobalt, chromium, molybdenum, even alumina, titania, even hydroxyapatite, what you can see that with changing the surface roughness as well as the composition, the cell density on the surface is also changes. That is also important to note. So here we can see that again there are different type of titanium alloys. So alpha and beta titanium alloy results in bone resorption and implant glue. That is why the different lower modulus alloys are introduced. I think it is also there in the market, but you know, if you have to purchase such type of alloy powders, the companies, if you see, only few are there. I think one of the companies, Goodfellow, I think you can note down, because Goodfellow is one of the best company. They are actually supplying these kind of different alloy powders. Okay, so if you want to purchase the powders, you want to process through powder metallurgy, so you can approach Goodfellow, which is a UK company, and they have a very good, what you call, repeatability in terms of quality of the powders. So here we can see again, as I said, the Halvard and Larian's combined concept to have improved morphological as well as biological fixation. So here we can see this is a porous implant, cervical and thoracic vertebra. So here the porosity is to improve the interfacial fixation. And also we mentioned the titanium implant, which is 3D printed titanium implant. Here different hydroxyapatite is coated to impart the bioactivity. So this is a maxillofacial reconstruction. Titanium mesh is used, even tantalum mesh is also used, and different type of hip design, where we can see they have introduced different level of roughness for tissue integration, and we can see the acetabulum Also they have roughness for tissue ingrowth, and we have a complete bone where also soft tissue ingrowth and the morphological fixation is also possible here. And this microstructure, you see, recent time you will see that a lot of literatures how to bioactivate the titanium surface. So I said to you that there is requirement of hierarchical, roughness and porosity. So now people are working on different type of techniques to have nano surface topography. I think recently my postdoctoral supervisor has published one article in scientific report just in 2015. Simply what they have done, they have taken the titanium and they have just done the autoclaving in sodium hydroxide, and they have shown that they have different type of nanorods, and if you have very needle type nanorods, they actually rupture the cells, and if the cells are much smaller in size, they give you antimicrobial property, because the bacteria and viruses are much smaller in size, they give you antimicrobial, antibacterial property. Whereas the cells are much bigger in size, they actually firmly adhere to the surface. Just by controlling the microstructure, we can control the antibacterial property, antimicrobial property, as well as cell adhesion property, improved cell adhesion property, and of course subsequently cell differentiation property. And this is the dental implant I already have shown you before, GMR dental implant, and this area they made it like a cortical to improve the tissue ingrowth. So this is again a very new field of material science, PEK, polyether ether ketone, which is introduced in the market. I think polyether ether ketone book has come fully on polyether ether ketone, I think back in 2012 or 13, and book has come into the market also. So you can see the series of implants now people are making based on PEK, but PEK is more like an inert material. To impart the bioactivity, they are using porous titanium interface. Even PEK based hip implants are also introduced. Now they have introduced 4th generation PEK based hip implant, where main stem is actually titanium, and in between they have PEK, and on the surface also they have titanium wires to improve the interfacial bonding. PEK based suture also has come into the market. PEK based cancellous bone is also there. So now we have cobalt chromium alloys. So mostly here you can see that castable cobalt chromium molybdenum alloy F75, and we have cobalt nickel chromium molybdenum alloy F562, which is produced mostly by rod forging. So here we have about 65% cobalt, 28% chromium, 5% molybdenum, and balance amount of nickel and iron. So there would be some minute amount quantity of carbon, silicon and manganese as well. So chromium is used for passivation. Okay, chromium is used for passivation. So as you dip this cobalt chromium alloy into nitric acid, they form a corrosion resistant chromium oxide coating. So nickel is used for increased strength, molybdenum is used for higher hardness, and carbon is used also for corrosion resistance property. So we can see here, so there are some implants, cobalt chromium molybdenum implants, tibial tray, and there are dental implants like bridges and by coping, metal coping they have done, and also dental implants as a whole, and also the hip implant where mostly the femoral head is actually made of cobalt chromium because it's very hard. So what we can see here, a series of metals and alloys are used for fabrication of implants. However, the bioactivity is not yet fully optimized. and that is why the easiest way to do is just to coat with different type of bioactive materials like bioglass, hydroxyapatite, etc., or different type of calcium phosphate like TCP, OCP, etc. But interestingly, most of the coating procedure, if you see the literature, they followed plasma coating, and by the power plasma coating you get really very thick coating. With time they chip off of this coating, and eventually the metal will be exposed to the body fluid. So that is why I said that there is a method for surface modification by Kokobu, which is we do some kind of surface treatment, surface oxidation, and then as you have plenty of hydroxide on the surface, so we can introduce very small, very thin layer of nucleation of hydroxyapatite or calcium phosphate layer, which introduces the bioactivity to the surface, and that coating could be very very thin, so that you don't need to coat very thick coating, so that you can avoid the chipping off. So there is another implant material which is nitinol. I think nitinol, everybody aware of nitinol, which is a set memory alloy, and here nitinol is basically an intermetallic compound, and here nickel and titanium equimolar mixture, nickel and titanium is used, and as you see that they have super elastic behavior because of austenite martensite transformation, and nitinol has one way set memory effect. So this nitinol is used for several applications including dental archwares, catheters, right, even stent. Interestingly, you see that nitinol has very interesting and non-Newtonian, non-linear stress strain curve, which is very similar to the tissues. We know that synthetic materials like steel, as they deform and yield, so there is a permanent deformation. But even in super elastic material like nitinol, though they have significant deformation, you can see the stress doesn't increase. Strain though they are increasing, but stress doesn't increase. So that way we can avoid the stress shielding effect because it doesn't increase above the critical threshold value. And that is why this nitinol is used for several applications. I am not going into the detail of phase diagram, but this is the area, this green area, where equimolar mixture of nickel and titanium. This composition is used for different type of products manufacturing, catheters, stent, super elastic needles, orthodontic archwares, files, for root canals, sutures, even clamping. So you can do the clamping because at 37 degree it will just memorize the shape and it will clamp on the side. So you can see, so this is a spring, right, and as you just pull it, it becomes almost like random shape, and that as you put in hot water, it again comes back, bounce back to its original shape. So that is a set memory alloy. So this set memory effect can be utilized for self expandable or the stent which can be placed by a balloon angioplasty. So what you can see here, some patients who has the problem of atherosclerosis, so there is a deposition of LDL, low density lipid, and that gives the plaque formation, narrowing of the blood vessels. So where the blood pressure, if the blood pressure is high, then blood cannot pass through easily, and then so there is an obstacle which may lead to thrombosis or rupture of the blood vessels. So in that case we need to place the stent. The stent could be of different type, like a bare metal stent, or it could be a drug-eluting stent, and usually this nitinol is one of the material which is used for such kind of application, and which is placed by balloon angioplasty, where catheter is used and X-ray guided or fluoroscope guided stent deployment is done on the site. So here you can see palatal arch or orthodontic distractors. So it's based on nitinol. So different type of filters, venous filters, Simon filters. Even we can see that endodontic files are also made of nitinol. Again, this is a very I think new introduction of this tantalum material. Tantalum nowadays also used a lot. It has a low modulus, as we have seen. Of course, very expensive. And tantalum is also used for cancellous bone, dental roots, even for knee, I mean the cup, as well as different type of other implants. So interestingly, this oxinium is anodized zirconium. That is also another implant material. It is, I think, introduced by Smith and Nephew. Oxidized zirconium metal. And this oxinium, I think I have heard in 2004 when a Smith and Nephew person was visiting our laboratory in University of Bristol. But the person who was responsible for development of this work was visiting our school in IIT Kharagpur, and I say, according to him, it has very good long-term follow-up study. So it has shown very good result. Specifically for mechanical movement, because it's anodized, it's very hard. So again, magnesium implant. Magnesium as a biomaterial, I think, is introduced in 2012, and today you see in 2014 there is a review paper on this. So lot of patents and lot of work is going on magnesium, and this is a wonderful material because magnesium reacts with water, forming magnesium hydroxide and hydrogen gas. And usually if you put the magnesium inside the body, it will be very toxic. But if you can form in the alloy, and if you can place, then the reaction can be taken care of, and it will have slow reaction, and with time magnesium can degrade away. So that is why there are several magnesium alloys, like we can see magnesium, calcium, magnesium, yttrium, niobium, zirconium, neodymium and zirconium. So there are different alloys are already introduced, and also stains, which is bioresorbable stains, are also introduced based on magnesium. I think it is still what is going on, not yet come to the market. And this is another area of materials. I think somebody was interested, somebody mentioned what about carbon. So I will not go into the detail, just I would like to say that if you see this kind of hybridization, kind of some sort of phase diagram, where you see carbon has sp3 hybridization, here you have sp2 hybridization, and here we have carbon hydrogen bonding. What you can see that sp2 hybridization forms the graphite and sp3 forms the diamond. So nowadays we want the implant where there is a mechanical movement is required, so you need some lubricating effect, as well as it has to be hard. So to impart both the properties, we can have diamond like coating, where you have some sort of graphitic properties, and also it has to be significantly hard. So that is where the DLC coating, diamond like coating, is explored for diverse application. So we can see that stained having DLC coating. We also can see different type of orthopedic load bearing implants, but as you see here, medical follow-up study is not much done. So now I would like to come to the polymers, and polymer we have two different type of polymers. One is a bio-inert polymer, and we have bioresorbable, biodegradable, right, bioerodible polymers. So usually the polymers which are having carbon-carbon extended chain, as I said yesterday, they are biodegradable or non-biodegradable. They are non-biodegradable because they do not have any polarity. They usually will not go for any kind of hydrolysis. So PEK, if you see polyether ether ketone, it is having carbon chain, but it has some carbonyl group also. Even then, it doesn't degrade. It's really hard, and it is a inert implant. Similarly, ultramolecular polyethylene, which is extensively used for hip joints and knee joints, where you have used the cup or tibial tray. Similarly, PEK, polyether ether ketone, is also used as a dental roots, also maxillofacial reconstruction, even some abutment for dentures. PMMA is used for dental root, and it erodes with time, and again you have to replace with a new implant. Here you can see the tibial tray is made of ultramolecular polyethylene, and you can see the acetabulum made of ultramolecular polyethylene. But also the contact lenses, intraocular lenses, are made of PMMA and polyhema, PHEMA. So these are also non-biodegradable bioinert materials. So PMMA is a hard contact lens or hard intraocular lens, whereas polyhema is soft or hydrogel type contact lens or intraocular lens. So we can see here the hard valve. Okay, I think we should be familiar with the Chitra valve, which is one of the cheapest valve available in the world, and this was developed by Chitra. We should be proud of that, definitely, because that is one of the finest contribution from Chitra. So as we know, otherwise, so valve is very expensive, and this valve, you see that main alloy, the ring, is made of cobalt, nickel, chromium, tungsten alloy, and the outer cover is made of PET, polyethylene terephthalate fabric. PET, polyethylene terephthalate fabric. Okay, polyethylene terephthalate fabric, and also we have the disc, which is actually ultramolecular polyethylene disc, which is used. Okay, this is a swing disc which actually opens and closes, and that is how it works like a valve. Stent, if you go through different companies, you will see that very recently people have introduced different bioresorbable stent, polylactic acid, polylactic glycolic acid, PCL. So different type of materials very recently. So Abbott vascular graft, which is also one of the stent which is introduced just in couple of years time, and the stents are bioresorbable or transient implants, so you don't need to remove, it's just degrade away. Similarly, we have nails or pins for bone plates. So these pins could be made of polylactic acid, which are bioresorbable. I'll just shortly tell you how and what property is chosen for making such materials. So also we have bioresorbable coating, bioabsorbable coating on the surface of the stent for drug eluting stent. Okay, so for some stent they use the drug. Okay, so drug eluting stent where bioabsorbable coating is used, and of course we know this Hemoflow or many other companies are there. This is what, can anybody tell what is this product about? No, do not know. This is used, have you seen in Aquaguard or Kent? But why it is Hemoflow? So whatever RO membrane is used for Kent, exactly same membrane, maybe of different materials, are used for blood dialysis. Okay, simply it is a hollow fiber. I think in our institute, Professor Santanu, he has lot of activities on this hollow fiber membrane. So polysulfone is one of the material used for making such hollow fiber membranes. Okay, for blood dialysis. Then of course we have different type of tissue engineered organs. What you can see, artificial trachea after 2 days of cell growth. So it is like you are making the organs in vitro. You are making the organs in vitro. You are making the human bladder, urinary bladder in vitro. So what you can see here, there was a BBC news that surgeon in Spain have carried out the world's first tissue engineered whole organ transplant using windpipe made with patient's own stem cells. So you can print or you can fabricate by any other means such type of structures, and you can isolate the cells, or you can have the stem cells and you can seed on these kind of materials, and you can differentiate into the tissue specific lineage, and then basically you develop the tissue in vitro in the laboratory, and which can be augmented at the site, and with time these materials can degrade away and cell synthesized materials will deposit, and gradually there will be regeneration. So this is very recent approach, and I'd like to mention that this is a very emerging field and highly interdisciplinary field, and you need lot of expertise. You need to have state of the art animal facilities, you need to have state of the art cell biology facility, and as well as you need to have very good manufacturing facility, and of course we need the help from the surgeon. Without surgeon it is impossible. Okay, so I would like to mention that in China lot of activities on tissue engineering, in Europe lot of activities on tissue engineering, even in US also they have lot of activities in tissue engineering. Very unfortunately in our country doctors are too much engaged in clinics because scarcity of doctors. Of course you have huge number of patients, so I think we need to work together with the doctor, and so that we can work in this area, and it can create a lot of opportunities. Of course medical tourism. So we can see the sutures. So there are different type of sutures available in the market. So of course we know there are non-degradable sutures, titanium even used, wires also used as sutures. So there are some polypropylene based sutures which is non-biodegradable. Chromic catguard, I think doctors are very familiar, and rather they can tell us what is chromic guard, which is basically a cat intestine which is cross-linked with the chromic acid, that is a chromic guard. So similarly ethylon is monofilament nylon. Nylon is a polyamide. Nylon is a polyamide, nylon 6, nylon 6,6, or there could be different other type of nylons. So these nylons are polyamides synthetically derived, and it is biodegradable. Similarly we have vicryl, polygalactine, we will see few more sutures. So polygalactine is synthesized in the laboratory and highly crystalline, and so it is degradable suture. So it's a classic example of two polymers, two monomers. One is polyglycolic acid and we have polylactic acid. So I think polylactic acid as well as the glycolic acid, these are all, I think polylactic acid especially are the components of Krebs cycle. I think I am correct, right? It's a component of Krebs cycle, polylactic acid. Yeah, so component of Krebs cycle. So it is very very nice approach if you can choose the material which is the component of Krebs cycle, which can degrade away by enzymatic activity. So using those kind of material, if you can make the polymers, so absolutely, you know, it doesn't give you much toxicity, and that is the nice way of doing the work. And as you see here, the structure of polyglycolic acid is CH2CO, and whereas polylactic acid has nothing but one more methyl group. So this methyl group gives you hydrophobicity, and in comparison to PGA. So this is polyglycolic acid moiety, and this is polylactic acid moiety, and polylactic acid is more hydrophobic than polyglycolic acid. Then if you do block copolymerization, I am not going into detail of block copolymerization. If you have a polymer where you are maintaining the block of lactic as well as maintaining the block of glycolic, this is a hydrophobic moieties and this is a hydrophilic moieties, right? And but PGA can easily pack themselves because they are very much linear, whereas in case of PLA we have some bulky group at the side. So PGA always give you very high degree of crystallinity, but PLA gives you more hydrophobicity. So by combining both in a different ratio, we can engineer the different level of crystallinity, okay, and hydrophobicity, and just by attaining very high degree of crystallinity, you can improve the mechanical properties. Clear? So if you have higher mechanical properties, it can be used for load bearing applications like pins, okay, but biodegradable. Similarly, we can make the sutures also biodegradable. But when you mix these two components randomly and you see the degree of crystallinity is 0, 50-50 PGLA. So it doesn't have crystallinity, it has lot of voids inside the structure, and these voids can be easily utilized for making drug delivery systems. So you can incorporate the drug into the voids and you can just inject. So you can have injectable drug delivery systems. Whereas if it is highly crystalline, it can be used for load bearing applications, and these highly crystalline materials can be used for biodegradable nails, sutures, pins, etc. Interestingly, you see the pluronics. This is very similar to PLGA. So where we have PLGA, hydrophobic group and hydrophilic group. If you have hydrophilic, hydrophobic and again hydrophilic, you can have core cell structure. You can make a ball, inside is hydrophobic, outside is hydrophilic. So you can combine two different type of drugs. In the hydrophobic side, we can incorporate hydrophobic drug, and in the outer cell you can have hydrophilic drugs. So depending on the requirement, you can deliver the drug sequentially at different locations and for different purposes. So pluronic is one of such product, where you can see polyethylene oxide, polypropylene oxide, again polyethylene oxide. You have hydrophobic core and you have hydrophilic cell. Similarly, you can have hydrophobic cell and hydrophobic core. So easily we can have different natures of drug in the same component. So here I am just showing the cartoon where we can have two different type of drugs. One drug could be used for closing the blood vessels, because in the tumor you have very leaky blood vessels will be there, leaky vasculature will be there, and if you deliver the toxic drug into the tumors, if there is a leaky vasculature, the drug can be released and it can go some other places, it could be toxic to the normal cells. But somehow if you can release the drug which will actually close the blood vessels, then afterwards you can add the cancer drug. So cancer drug will be confined to the tumor site and it can help the apoptosis of cancer cell, and that is important for cancer therapy. And also it can be used for different contrast agent. So I am talking about bone cements. I think everybody should be aware of bone cement. We know that for bone cement PMMA, polymethyl methacrylate, is used, but it is not just polymethyl methacrylate alone. It is also mixed with some unreacted methacrylate, and some amount of barium sulfate is added. Barium sulfate is added to impart the radiopacity. But this barium sulfate is the culprit which can glitch out to the sides and can activate the macrophages and which will cause osteoporosis. So that is why this bone cement is good but causes a lot of problem. And interestingly, if you have a revision surgery, I think you need to ask the doctor the situation they face. So revision surgery is very, very tedious because PMMA will set and it is very, very inert. So it doesn't have any room for remodeling. So basically they have to take off the implants like the carpenter is taking off the nails from the wood. Okay, anyway, so now there is a fourth generation biodegradable cements, bone cements. This is still clinical trial is going on. Okay, what we can see here, this is a fumaric acid reacted with propylene oxide, and as you can see here, this is a copolymer of propylene oxide, fumaric and propylene trimer, or you can have, this is a, one is fumaric acid, another is maleic acid. So propylene glycol and maleic acid, and again propylene glycol. So maleic, propylene, maleic, you can have trimer, and then subsequently as you react with further with maleic acid, okay, so you can get the polymers. So this you see the polymers, this is a polyesters, this is a, can you see this, this is a polyesters, right, this is a polyester, carbonyl and O, this is a polyester group. So this polyester group, so this is a polyester polypropylene fumaric diol oligomer, further they have the double bond. This double bond can be further explored for cross linking. So when you have this such material, as you mix with ammonium persulfate and tamate, they further react and they set at the site, and this ester group with time gradually degrade away. So with time the cement can degrade away, and if your implant is highly porous, so that at the surface, so that tissue can, with time tissue can remodel and it can have ingrowth into the implant, and eventually you have complex biological fixation. Okay, so now I think I'll go little fast. So here you can see skin. I think skin is one of the organ we know, I think largest organ of human body. I think doctors will be suggesting me. So largest organ in the human body, and I think it always experience a different type of trauma, injury or assaults. And in our country specifically, we have huge number of burn patients. So skin graft is eventually, or burn dressing, skin or wound dressing is eventually a very, I think, hot topic, and it is possible to translate also very easily this kind of technology, because you know in our country, I think I already discussed, the ethical clearance is a major problem, and we still not yet clear what is the drug and what is implant. We do not know actually, because we have everything under DCGI. So we need to take the problem which we can, if you really have to translate, if you have the intention to translate the technology, we need to take the problem which you can deliver in say 5 to 10 years. And in that case, I think skin is one of the important subject to work with. Similarly, the dentures, not the root, I should say the crown. I mean, when you say root, again there is a lot of ethical issues. So, but skin is really a very complex organ. It has multiple role to play. But interestingly, you see the skin structure, there are bilayered structure. You have the basement membrane, above that there is a keratinocyte, and keratinocyte has functionally graded stratified keratinocyte layers, and underneath of the basement membrane we have connective tissues. Okay, and this basement membrane is act like a limiting membrane, and beyond that there is no blood vessels. So the all cells survive, specifically the keratinocyte layer, through diffusion. So that is the structure which you have to consider while you are working on skin. I think just I will show you a little bit of some work we have done long back. So we have isolated collagen from different sources, and this collagen we made into different type of fibrous structure, and we have made some nanofibers by electrospinning. So we combine the collagen and electrospun layer, and we have applied it to animal, and we found it is giving us promising result. The student who has done this work, Dr. Soumi Desorkar, I think now she is working in Himalaya for quite some time now. So what she has, this work she has done in Australia. She was in fellowship in I think University of Queensland, and so this is a skin equivalent model. So what she has done, she has collected skin from the human, and of course you have to take the ethical clearance, and after that she decellularized this skin, and then again she seeded the fibroblast followed by keratinocyte. So once the fibroblast is seeded enough, then she applied the keratinocyte. So keratinocyte, once they are confluent, they apply the pressure, that fibroblast goes in. So you have now the structure of the skin. So it is a skin extracellular matrix, and you are now, you have developed a model which is skin equivalent model. So why we do that? Because skin always has a chance of infection. To avoid that, what we do, we seed the cells, we sterilize the skin, and we decellularize it, and then we develop the skin equivalent model. Then we do the punch biopsies. So after that, what we do, we place our scaffold in between the gap and try to see whether our scaffold is able to promote the keratinocyte layer migration. So what we can see, there is one scaffold where you can see, so this hematoxylin eosin staining, the pink color says the keratinocyte layers. So what you can see here, just a electrospun nanofiber seed, it doesn't have keratinocyte migration. In this layer, when we have some amount of collagen, we see that very nice keratinocyte migration. So we, from this study, we understand collagen certainly helps to migrate the keratinocyte. That is very, very important aspect for wound closing, as well as wound healing. Okay. So similarly, nowadays there are many different type of products are available in the market. So one is epidermal product, cultured keratinocyte layer for epidermis formation. So you can imagine like Epidex, which is a cultured epidermal sheets. So there is a polymer matrix or the membrane on which the keratinocyte was cultured, and it's a confluent layer. It's like a seed, which is basically a keratinocyte seed, and you seed on the side, it just integrate. This is one of the product available in the market, Epidex. So now you can imagine in the medicine shop of pharma industry, so you can have organ in the market. Okay, so people are selling the organs. So this could be one of the emerging area. So eventually it gives you lot of job opportunities. Epidex is a cultured epidermal seed from hair follicles. Cultured epidermal seeds from hair follicles. My skin subconfluent cells on bovine coated polymer membrane. I remember in 2012 I was visiting a conference, TARMIS Asia Pacific meeting in China. So there was a session for students. A lot of scientists, couple of renowned scientists are interacting with the students. So one lady, she actually working in a laboratory. She was a scientist. She was working in a laboratory, and suddenly one patient came. I think 5 years old boy. He had almost 80% burn, and she did not have anything in his hand for the treatment. So what she has decided, she has just taken a membrane which is used for filtration, and she seeded the keratinocyte and just covered on the patient, and she got a wonderful result. And with that, she thought, now let's go for the marketing. So this product she has marketed, and she, I think, has earned a lot of money. Now she has a company, and which is, I think, it's a huge company now. So you can imagine, just anytime you are coming across any problem, and if you find nothing is available to you, and if you find okay, this might be a solution, you should explore that and try to come to the end and see the conclusion what more can be done, and finally you may become entrepreneur one day just by a simple thought. Okay, this is my just suggestion anyway. So there are dermal product. So for 2-stage skin replacement, I think I can shortly I can tell you some other story that will be also interesting. So dermal product, 2-stage skin replacement. So Permacol is one of the product, dermal collagen from human allodermis or porcine dermis. Okay, Dermagraft, bovine collagen with nanoven polygalactic acid with silicon. Transite is also bovine collagen based nanoven polymer, biodegradable polymer with silicon membrane. So these products, actually skin is a external organ, always they encounter different type of bacterial attack or fungal attack or even virus attack. So that is why when you are applying such dressing, so you have to have very nice covering. So here you can see they have used the silicone rubber as a cover. So once it is integrated on the dermis side, then you can peel off the silicone rubber and you can spray the keratinocyte layers so that it regenerate much faster. BioBrain is one of the product. You can silicone embedded in nylon mesh and chemically bonded collagen is there. Integra, bovine tendon collagen with gags and silicone. So these are the products in the market available. I can say these seeds of 1 feet by 1 feet will be more than few thousand rupees, like 50,000-60,000 rupees. It's very, very expensive products. Okay, so but easily we can manufacture here in our country. Okay, but we should have proper DCGI protocol so that we could be able to make the product, we can deliver, and we can reach to the patient, and finally there will be benefit from either side. And interestingly now in this area I would like to mention lot of activities are going on how to print directly on the wound bed. Like you imagine, like in the warfare zone, so that there is a soldier who has injury, right, and I have the stem cells which has less immunogenicity, maybe some kind of placenta derived stem cells, and then we have the material and patients are lying on the bed, directly we can print the cells and the material together on the wound bed, so he recovers much faster. So that is the kind of technology are emerging now. Okay, so we need to think that how so bioprinting, this is I think termed as biotrip printing. So this is a very new and emerging area, and I think already you have seen this kind of news in the newspaper. I think this is a Chinese boy, and this news was I think almost 6 months back in the Times I have seen, and this is a huge controversy when you see that mice has a ear. Okay, and this is 3D printed and then seeded with the cells, and it's augmented into the nude mice, and once the cartilage has formed, this was removed and it's surgically attached to the human. Okay, similarly you can see here the nose which was developed on the forehead, and it was removed and it was grafted on the patient. Okay, and I can tell you another story. I think in 2012 conference I visiting China, I saw people are growing teeth on the forehead. Of course it is in China. Okay, they are doing in China. Okay, even Europeans are also very surprised how it is possible. They have just taken different extracellular matrix from the root and they have augmented there and they started growing as a teeth. Okay, so you can see the blood vessels. Okay, so soft tissue blood vessels, and these blood vessels, they have different type of circulatory systems. You can manufacture using polymers, you can extrude, and here also you can use the stain in combination with the metal and polymers. I think already we discussed the intraocular lens, IOL lens. This is IOL lens, bioresorbable sutures, and of course we can have a bionic man, right? So all the implants can be made and augmented, and still person survive, and and thank you.
Hmm. Mm. Now, I am going to start the second part of my lecture. It is not the second part, but the separate topic, that introduction of porous biomaterials for custom made implants. Why we want to introduce the porosity? That is very important. For any implant, what we are observing, that you have seen already, that there is a bone and you are introducing the implant. Okay. Now, there is a huge mismatch of these two materials. Those are coming into the interface, interacting with each other. That is the implant that is made of metal and bone. Chemical side I will not go, but mechanical properties, if you see, there is a higher Young's modulus and lower. So, and there is also some motion in between. So, all these complicated phenomena, if we want to resolve, then the best solution is that from the mechanical point of view, we have to keep the stiffness of the implant close to the bone, especially surrounding bones. But it is to some extent impossible. Why impossible? That I will tell you later on. But to us, just now, whatever technology we have in our hand, it is to some extent impossible. Now, so how we are trying to resolve it, or we are trying to provide the solution by reducing the stiffness. How? The porous material is one of the solution. If we will provide this type of porous structure of any metallic, what I will say, that material, then what will happen? Its stiffness will be reduced. It is known to us. If we can use that properly, then we can get a solution of it. Now, and another possibility is there. Due to porosity, there is a chance of osseointegration more than a solid one. Osseointegration means bone growth, and through that porous holes, if we can keep the porous within a certain limit or certain size, what will happen? The bone can grow properly. And even if we are thinking in this level, that if we can keep the interconnected porous, means the porosity will remain and they are connected, then the bone growth may go that far that vascularization is also possible, that level. Okay. Then what will happen? It will be a just like integrated part of the body. That is the goal. Well, but here the research is going on still in the level of that how to reduce the stiffness only. So just what we are trying to mimic the bone. That is the why. Next, because you see the bone structure here and here, there is a change of density. And you have learned it, that why there is a change of density. We have done the finite element analysis of it. Professor Gupta has already shown you probably. There we have seen the density is very much related to the stress generation. So it is so well engineered. The direction of these cancellous bones or the structure is something like that. If we see microscopically, it is placed in such a way, its orientation in such a way that that's in the direction of the load transfer. Okay, so that is the finest level of and highest level of composite material for the load transfer. So to reach at that level is too tough. You can easily understand that when you are taking just one bone piece of, and if you take the titanium alloy in your hand, you can easily compare that what is the difference of weight. So bone is lightweight material compared to any metal, but it is taking this much load due to this property that its directions of the, what I will say, that cancellous bone is such a way it is oriented that it can take the load in a proper direction. There is two types of bone, you know already, that cortical bone and the cancellous bone. Cortical bone, there is, I am not going to the detail of it, but you know that is to some extent compact, and there is blood vessels, osteons are there, herbation canals are there. So that way they are getting the nutrients, all these things. I am not going to the detail of it. And as well as you know about the cancellous bone. The cancellous bone are 50 to 300 micrometer in diameter, and the, what I will say, that it porosity ranges from 75% to 90%. You see that much porosity, it is aligned, but it is taking a huge load. That I am telling about the cancellous bone. Mainly by this porous material, we are trying to replace the both. Okay, that I will tell you later on, that changing the porosity, gradation of the porosity, we can replace the cortical bone as well as the cancellous bone. So this is a sponge-like appearance formed by the plates of bones called trabeculae, and we are trying to replace that, and that is oriented along the stress line that I have told you earlier. And what is the beauty of it? Provides strength with a very light weight. So that is the beauty of it. And I am not going to the detail of bone of it, already you have learned about that. This is the bone structure. Probably each and every speaker has shown you. Now, another thing is very important. That is anisotropic in nature. Means in one direction strength is high, but another direction it is weak. So it is so much light. So in the porosity, how we can maintain it when we design, that is also very important. What is that? If you see that in tension compression for the all materials there is a difference. Here that for cortical bone that will depend on 79 to 151 in tension, always tension, weak in tension and strong in compression, 131 to 224 MPa the compression, the strength of the bone. But in a transverse direction it is very weak. See, almost 50%, my mind close to that, 40%, something like 51 to 56 MPa, and in tension, and 106 to 133 MPa. You see, 133 MPa. So, transverse direction, the Young's modulus or strength, all these things are very less. If you see that compact bone also, in the direction of the load, it is 17 to 20 GPa, sometimes more than that, 24 GPa in the longitudinal direction, in direction of the load bearing direction. And the transverse direction means anti-degree of it, opposite direction, it has come down to 60 to 6 to 30 GPa. You see, so less. And on the other hand, if you see the cancellous bone also, it ranges from 2 to 5 MPa and elastic modulus is 0.76 to 4 GPa along the load transfer direction. On the other hand, you will see that transverse direction it will be less. Now, the biomaterials that we are using, that is the metals, polymers, ceramics, composites, and the natural materials. We have to see that ceramics and polymers, you cannot change the mechanical properties, but for the metallic one, you can change the material property by using some alloy and other way. We can make the high strength, high ductility, fracture toughness we can increase, hardness, permeability, all these things. And I have already told you that in a decrease in elastic modulus would result in a higher elastic elongation of the cells in the vicinity of the implant, and whereby stimulating bone formation, what is called the osteointegration that I have told. Now, which are the materials that people are using? Cobalt chromium, stainless steel, titanium and its alloy. But what is the most suitable from all these directions? We have seen what I will show you the Young's modulus. If you see that whatever available biomaterials means mostly, if you see that here there is a comparison between the metals, that cobalt chromium, stainless steel, titanium, alpha beta alloy, titanium. So among this, if you consider the metallic one, the titanium is closer to the bone, though there is a huge mismatch. Okay. So, if we want to go for porous design of metal, which one is the most suitable? The titanium one. Okay. So, we have used the titanium, and titanium and we have tried with another type of material, and we have observed that titanium is giving us, means we have made the porous of the stainless steel, not the made, we have simulated, and we have made only the, we have fabricated only the titanium one, that I will show. It has a high strength. What is important? For what we want, Young's modulus will be high, strength, Young's modulus will be low, and strength will be high. That is the basic thing for design a biomaterial. The basic thing. What is this? Young's modulus low, so that it will provide high strength, but it will not fail. For that, it will require high strength. So that is the main criteria for a what I will say designing of implant material. Now, we have done this in a two parts, two aspects of it. One, we have designed it, and we did the experimental validation of that. We have designed different type of porosity, simulated, and we have observed the result. Another way, we have done some experimental validation. What is the objective of the research? To analyze the impact of pore morphology and porosity on implant materials, find out the E effective. What is the E effective? What is the Young's modulus? Stress by strain. Sorry. Hey, yes, stress by strain. Hey, sorry. Yes, yeah, stress by strain. And then, what is the E effective? E effective is, if we make the porosity, then we will get the actually stress and strain, those both are we are calculating. No? But if we make the porous one, if we apply load, we will see the deformation, and it's in one direction, then we will find it out the length on that direction, and that strain we will find it out, and we will find it out the stress by P by A. Is a basic thing. So if we made it porous, then what is the change in this direction? Because E effective means we are making it by titanium, na? We are not changing the material. But when we are producing the porous one, then what is happening? If you apply the load, actually next slides we will get it. Here, you see, it is, suppose it is solid one. If we apply the load here, okay, if it is solid one, its deformation will be something. And if it is porous one, you see that there is holes. Okay, you have observed the holes. If it is hole, and if you apply the load on it, the deformation will be more in this case. Okay or not? Okay. So for that we will consider the strain will be different. But for the same load, so what will happen if the strain will be more? Then we can consider, if we divide that stress by strain, the E will be less. The strain is more means E will be less. Yeah. So that is the E effective. Okay. That term is very important. I have to use it time and again. Okay. So that we have to make less. and we will consider that E effective is the actual effective, actual what do you say that real life Young's modulus of that porous material. Okay. So E effective, and we have optimized it that for which pore size, for which percentage of pore we are getting the best result, and we are done it for compressive, tensile, etc. Then for bending, torsional, what is the effect of it? Huh? How it is changing the stiffness for the porosity. But what is the danger of using porosity? Obviously, if you apply a force on it, you know the stress concentration will come, will generate because you get this porosity, and that may lead to failure. So we have to be careful, because we can make any level of porosity, we can go. But what will happen if you apply force and there is a stress concentration, and if there is a crack generation that will propagate, ultimately it will lead to failure. So we have to optimize that. So it will, Young's modulus, effective Young modulus will come less, and we have to be very much careful about the stress concentration level. That due to that porosity, what is the stress concentration? That should not be, that should be within limit. So what we have taken a 20 millimeter 20 millimeter cube. We have made it solid, and we have considered different percentage of porosity, means 10%, 20%, and high porosity 35% to 40%. And we have observed how we have made those porosity spherical and with variety of dimension. That, and what will happen if we have kept the pore percentage suppose 20, and that pore percentage we can meet with different diameter of pore. Okay, you can understand my point. You can take number of holes, you can vary, means if you 64 big size pore you will take in the cube, that will be made 20%. Another way, if you take 216 number of small pore size, the effective porosity will be 10%. Maybe happen. Okay. So that we have taken, means what I want shown, that is solid cube and that is the porous cube. And the boundary condition is that here we have made it fixed, and here we have put it, and we have taken different, here we have applied the load, and inside the we have kept different type of porosity, means different, that we can see then later on. See, here we have seen the picture, means just stress contour of this solid one, but if I will cut through this section, we will get that view. What is this? It is telling that here at the porous surroundings there is a stress concentration, and we have to find it out, that what is the stress concentration. Okay, so which one, due to what is the effective stiffness due to this porosity, and what is the stress concentration level. Now what we have observed, if I will take the titanium, it is close to 117, you see. Now if we will take the 10% porosity, means this line, we are getting close to 85, something like that. Okay, you see. And what does it mean? It is the size, number of holes 4 per line. What does it mean? We have taken a cube, and 4 holes. If we will take 4 holes and meet that 10% porosity, and we then if we will 8 holes means the dimension of pore diameter is less when it is 8. Okay, and here the dimension is more, means pore size is big. Okay, but what we have observed, for this there is no effect. Means if we take big one pore size but small one pore size, but the pore percentage is same, 10% porosity, then we have observed no difference in what I will say the effective modulus. Clear? Now for 20%, if you see, that has come to the what I will say 65 or something like that. Then for 30% we have observed it is 57 or something like that if you take the average. 40% it is coming down to 50 something like that, and for 40% is less, 35% is so 40% it is coming closer to the place. But next you will see the stress concentration. It is happening that if 40% porosity, the stress concentration is high. But what is important, that if we will see that higher the higher the porosity, higher the stress concentration. So we have to optimize here that stress concentration should not be go a limit, and it should be done in this way. So we have made a that is the we have considered pore efficiency, the term we have used, that one end we have kept that effective modulus, another the stress concentration, and we are getting a very good result at 35%. Yes, 35% porosity. There we have seen that we can, what I will say, that optimize it, that where we are getting there is we are getting less Young's modulus as well as moderate level of stress concentration. Okay. Now this is the for simply tension compression. For bending and torsion, we have considered what we have done, same level. You see, this is the pore, that this beam we have taken, consider, and making this type of pore inside it. Okay, throughout this, and regular. Actually, that is not happened, but we are for the simulation we are doing it, and we have applied the distributed load, and you see the result. I am not going to the detail. What I want to say, see that if I will take a section of it, these results are coming. Yes, at the end level, obviously there will be higher stress. You know that for bending, and but what we are observing actually, that there is a typical one due to the, and also torsional level. But if we apply the torsion, and there we are observing certain stress phenomena diagram, but which one is very important? Here we are getting that if the stress, the stiffness or the Young's modulus is varying with pore diameter. Sorry, bending stiffness is varying with pore diameter. What does it mean? Why it is happening? Last time in the case of tension compression we have seen no effect, but in case of bending stiffness there is an effect. Why? Those who are mechanical students, they should understand it. I'm telling you, for that, for them. What is that? You see that stress is equal to m by z. Okay. Stress is equal to m by z, and m by z means I is a factor. I means moment of inertia. So if the whole diameter will change, dimension of the whole diameter change, then what will happen? I will change. If I will change, that is the effect on stress. Okay. So in case of bending, we have observed that whole diameter has its effect on the effective modulus. Clear? Now I am not going to the detail of it. Now how will you manufacture it? I have shown you the detail. There is a machine that is called LENS, laser engineered net shaping technology. How we are doing it, that is important. One end we have the titanium powder we are supplying through this, here, and there is a laser beam, laser gun is there. So according to the program, the powder will be poured and laser will melt it, laser beam will melt that powder, and it will, you have to allow some time for solidification. In this way, you can make any integrated shape, any porous shape. Okay, you can say this is the additive manufacturing technique. And CGCRI, you know that they have that machine, we do not have, and we are collaborating with them, and they are providing us this technology. And in this way, we can make the solid one layer by layer. Okay, you are putting the powder, you are doing it, and another way you can do it by layer wise in this way. Suppose you have to make the porous one, then you have to go for this. Okay, first layer in this way, second layer in this way, third layer in this way. So you will get some interconnected pore. Okay, here. Now we have made it, fabricated it. Okay, then EDM machine we have cut it properly so that we can go for testing. And what we have done after making those samples, okay, these samples here, we have done the microcity. Okay, and we have done the microcity, and that microcity images we have placed layer after layer. Okay, and layer after layer we have placed it, and we have got this level of meshed model in the microcity data, and we have provided. So we have the actual sample and we have the simulated one, means the model of those from the microcity. Now what we have done some simple model, that is a design model. Okay, so where we have provided 10% porosity, 10% porosity, but through the easier model. And what we have done, that is the already, if the total 20% porous titanium that we have told, and if you cut it at level, and you will get that level of porosity. Okay, now we have measured it, and this is the microcity that we have modeled. I am not going to the detail of it. Now it is a 10% porosity, it is a 20%, and we have done the analysis of it. Okay, that finite element analysis, and also this Harvey model, that easy model that we have made through model. Okay, and what we have observed, that so from this point we have got some results, that how much stress strain is occurring, and we have done the experimental one. Okay, now what results we have got, that is, we have seen that according to our simulation, we have got the 0% experimental result, this one, and the RV model, means simpler model, we have got this one, and for microcity model, we have got this one. So what we can say that why we have done it? Because all the time it is not possible to make the, what I will say, the porous material fast, then we can go for experiment result. It is given us confidence that without fabricating the material, if we can simulate the materials of our own in our computer, we can predict the what should be the material property of it. Clear? Okay. So that will give us confidence that yes, if experimental curve will be something like, it will be 5 to 10% different of this. So this 5 to 10% difference is allowable. Why? Because total engineering science is going on two words. What is those? Assume and neglect. So neglect that 10% of it means okay. So you should remember it always that whenever you need, you can assume something. Whenever you need, neglect. So in this way, you will see. Okay, so here we can neglect this 10% difference. So what we can do that we can yes, we can design the material of our own in the computer and we can do it. So, and we have used it in our dental implants. That is the application. Is a see the city value, city data. You know that, and we have made the models. You see, in this way, you know that from the city data how we are making the model of the mandible. Then we are fixing the screw of the solid one, and here in the mandible, and we have given the material, assigned the material property, and we have given the loads on it, and 100 numbers of models we have analyzed, and we have observed the results in the bone, etc. Actually, the same thing that you are observing for last 3-4 days, that series scan data, model, then apply load, then see the results of stage drag contour, and modeling of those. And this is the we have made the models of porous implant. Okay, and we have analyzed it into the, and we have seen the results. These are the sample implants. So I'm not going to the detail. Only thing I will. This is going to be the next generation, and you have seen the pictures of the previous lecture. There also they are going on that level. They are actually fabricating it. We are simulating it. So and something I will discuss on the spinal implant also. We are making the functionally graded material. I'm not going to the detail of it. Yes, in the disc here, we want to make the disc. There we are making it by ultra high molecular weight polyethylene. Now, if we can make it porous, then what is needed? We need more deformation at the side level. Now, so we can make it by functionally graded material by using porous. So what we are doing? We are observing the results to this porous, and then we have observed the stress analysis of those, and effective GPA is increasing with the porosity. It is a ultra molecular weight polyethylene. Then radially we have varied the porosity. Means inside there is 10%, outside there is 20, 30 in this way, graded, functionally graded. Okay, according to our need. And what we have observed, we have did the analysis, and we have got good results. Why we need it? Because at the time of whatever the flexion or extension, we need more deformation at the end side, and middle level we do not need that much. So we have made the functionally graded. So we have got these results. Final disc, we have varied the material property, LDLE. And thank you for your patience here. Yeah.
I'd like to present this to you.
Thank you.
It's a souvenir.
Thank you, Professor Gupta. He is my friend, so I cannot say much about him. But he is one of my best friends. You know that already. But it's my privilege